Okay, so today, since you have no homework due or anything, what I'm going to do, I'm going to solve the midterm for you and see that if it is doable in less than an hour or not. So, and there is a typo in the solution, so you might want to have the correct solutions too. So don't worry, you haven't been graded based on the typo. How many of you? How many of you have looked at the solution? Okay, very few. Very few. Okay, it's good. It's good. Okay. Was it hard? No, this is an honest question. Was it hard? Was it hard or long?
It was very long.
Both. Okay, so let's time it and see how much does it take. I'm not going to go fast, so it would be fair timing. So we start at 4:05. So let's look at the first question. It's saying consider the following simple LP. Maximize x1 plus. Hey, we had an arrangement. Those who want to talk on the back, those who don't want to talk on the front. So just go back and talk. It's totally fine. 2x1 plus 3x2 is less than or equal to 20. 3x1 plus 2x2 is less than or equal to 20. x1 is less than or equal to 6. x2 is less than or equal to 6. x1 and x2 are greater than or equal to 0. Okay, so the first part was to draw this one graphically and find the optimal solution graphically. So if you had drawn a nice picture and an exact picture, then the question would have been extremely easy. You even didn't need to go through and I'm going to tell you how I graded. So if you listen to it and then you saw a discrepancy with what I say here, how I have graded it, and you haven't been graded based on that, you can just tell me when you get back your paper and I would correct it. I'm sure that I have made mistakes in grading. So you just needed to draw this in a. Unfortunately, I don't have a ruler here. Otherwise, this would have been even easier. So the first constraint that I'm worried about is x2 less than or equal to 6. So this is x2, this is x1. Then we have x1 less than or equal to 6. 1, 2, 3, 4, 5, 6. Then we have 2x1 plus 3x2 less than or equal to 20. So one of the points that this guy passes through is 4, 4. 1, 2, 3, 4. 1, 2, 3, 4. And another point for this one is you put x equal to 0, x1 would be 10. Unfortunately, I don't have a 10 here, but it would look like something like this. And the other one would also look something like this. It would have been easy to draw the second one if you have drawn the first one, because it's just, you have to flip this and get it. Okay, so we have these 4 points. This is something beeping? Hello? Are you beeping here? Okay. And I guess the beep has nothing to do with us. So, now, so this would be our feasible region. With 1, 2, 3, 4, 5, 6 corner points. 6? 1, 2, 3, 4, 5, 6 corner points. Now the question is asking you what's the maximum. So there are different ways to do it. Some people have drawn a line, this line, and then started moving it up and up and up, which would be a line like this. So the line would exit the feasible region at this point, and they have said that this is the feasible, this is the optimal point. That's one way to do it. This is totally correct, nothing wrong with it. Or the other way is just the coordinates of this point. This is 0, 0, this is 0, 6, this is, 6, 0, this is 6, 1, This is 1, 6, and this is 4, 4. If I'm not mistaken. Now, the other way is to just plug these numbers into the objective value and check it. So we do that fast. A, B, C, D, E, and F. So we go for point A. The objective value would be 0 and 0. You put it there, it would be 0. At point B, the objective would be, this point is 0, 6, 12. At point C, it would be, for example, 1 plus 2 multiplied by 6, it would be 13. At point D, it would be 4 plus 2 multiplied by 4 equals 12. At point E, it would be 6 plus 2 multiplied by 1, it would be 8. And at point F, it would be 6 plus 0 would be 6. So this would be the points that you have, and the optimal is trivially this one. So this would be part A. Part A also asks, is this unique? This is unique, and the reason that it's unique, some people have written because it's a corner point. It's not unique because only it's a corner point, but because it's a corner point and no other corner point has that value. Because if it's only a corner point, that's not enough reason to say that it's unique. Now, the second part says, write down the dual of this problem. Now, writing down the dual of this guy would look like this. Minimize. It's a maximum problem, so we call it the minimize problem. Then you assign V1 to this, V2 to this, V3 to this, and V4 to this. So these would be the 4 dual variables. Then you start writing down the first, you can write down the objective function, which would be 20 multiplied by V1 plus 20 multiplied by V2. So 20 V1 plus 20 V2, subject to, now, 2 V1 plus 3 V2, now, plus 1 V1, but let me write it this way. Now it's more easier to see. 1, 1. So when you multiply 2 V1, 3 V2, and 1 V3, so it would be 2 V1 plus 3 V2 plus V3, and then 1. The sign of it is, since this is greater than equal to 0 and it's a maximization, it would be a greater than equal to 1. And the same way you write down the second constraint, it would be V4 greater than equal to 2. And V1 and V2 and, V3 and V4 are all of them greater than equal to 0 because these are all less than equal constraints. So this would be the dual. Now this is part B. In part C, it asks you, given using the complementary slackness conditions, find the feasible dual part. Okay? Now, the dual point, the optimal dual point. Now, let's see what we have. By complementary slackness, we have x1. Oh, let's write down first the complementary slackness for this one, for down. So it would be v1 multiplied by 2x1 plus 3x2 minus 20 would be equal to 0. Of course, these are all star, meaning that this is at optimal point. You have v2 star multiplied by 3x1 star plus 2x2 star minus 20 equals to 0. You have v3 star multiplied by x1 minus 6 equals to 0. And you have v4 star x2 minus 6 equals to 0. Okay? Now let's see what we have here. We know that the optimal solution is x1 equals to 1, x2 equals to 6. So here, x1 equals to 1 would make this thing to be 1 minus 5 minus 5. To be equal to 0, we need to have v3 star equals to 0. So this is the first thing that you get. The second one is you put these guys here and see which one of these two constraints is not binding. You put them here, you will see that this one is not binding. It would be 3 multiplied by 1 plus 2 multiplied by 6, which make it 3, 6, and 12, 15. 15 minus 5. It's not binding, so then v2 star has to be equal to 0. Now, you know these two are equal to 0. But these two guys would turn out to be not binding, so you don't know anything about v1 and v4. Now, to find v1 and v4, we do the other way around. Remember, the primal problem is the dual of the dual problem. Okay? If you write down the dual of this problem, it would be a maximization problem. You would assign x1 to this, x2 to this constraint. Write down the dual. This would be the dual. Okay? So we write down the complementary exactness conditions for this guy now. So we will have x1 star 2v1 star plus 3v2 star plus v3 star minus 1 equals to 0. And we have x2 star 3v1 star plus 2v1 star plus v4 star minus 1 equals to 0. Okay? Now we know that this is not equal to 0 and this is not equal to 0. So these two terms have to be equal to 0. Now we also know that v2 star equals to 0, so this is 0. We know that v3 star equals to 0, so this is 0. So this is 2. And this is also 0. And everything is, and the whole term is also equal to 0. So you will have 2v1 star minus 1 equals to 0. And you will have 3v1 star plus v4 star minus 1 equals to 0. This one would give you v1 star equals to half. This one will give you v2 star equals to half. So, sorry, v4. Okay? So you have a dual vector which would be v equals to 0, half, 0, 0, half, which is a feasible point because all of them are positive. Okay? So you have found a set of x's and v's that satisfy complementary slackness, that are dual feasible, that are primal feasible. So they are optimal. Done. Now, the question is this unique or not? It is unique for two reasons. You have to say both of them. First, you have only a unique optimal. Thus, if you have a unique optimal, you can only write one set of equations. And this set of equations has only one solution. It doesn't have two solutions. So it's unique. It's possible that when you write down this set of equations, it turns out that these are linearly dependent points, and then you have multiple solutions. Then you say it's not unique. But here you just solve the equation. There's only one solution, so it's unique. So but they're unique, and that's it. Questions? So this was the first question. It took us 10 minutes. Yeah. So we are now at 4:15. We'll start the second question.
What is it meaning that pick up any optimal point?
Oh, well, the question didn't want to tell you how many optimal points there. If it said pick up the optimal point, then you would have known there's only one optimal point. So when it says pick up any optimal point, yes.
For this optimal point, there's only one. The basis is degenerate here. So
Here is not degenerate, no.
in dual.
Oh, this is not. This is the objective function, the green one.
The vector v, half, 0, 0, half.
Yeah, because these two are the basic solutions. These are the basic variables. These are the non-basic variables. There are two constraints here. Okay. And since we haven't talked about degeneracy, I thought you wouldn't need to worry about that during the exam. Now, the second part is the inventory control problem. This might be said that this is the hardest question in the exam, I would say. Which, well, it still isn't that hard, but was tricky. So let's see how this one worked. Now, this one said global minimum manufacturers bikini swimming suits. Their business is highly seasonal. Let me change my marker. Yeah, it's highly seasonal. Sorry? Oh. With the expected demands being okay. So for the next 4 months, month 1, 2, 3, 4, 5, I start 4. We have the demand $500, $100, $2,800, and $850. So these were the demand values. Now, the company can produce, capacity is 1,200 per month. Okay? Per quarter, sorry. These are not months, sorry. Quarter, and this is per quarter. Doesn't change anything really, it's just that to make it, you can guess that this is summer. The The cost of holding inventory, is $15 per dozen per quarter. These are all dozen, and this is also dozen, so that the units match. Otherwise, you have to multiply by 12 somewhere. Global minimum wants to meet demand while minimizing the inventory cost. Formulate an LP to choose the optimal production for just the next 4 quarters. Okay. Since we are looking for the optimal amount of production in the next 4 quarters, the most natural variable that you can think of is how much to produce each quarter. We use them, we see later on if we need something more or not. So we would be writing so assuming that we produce xi in each quarter, let's write down the constraints. For the first month, we will have xi, whatever we produce, is greater than equal to how much? 500. Okay? Then for the next month, what would be the amount of bikinis that we have in the next month?
The production in the next month.
Whatever we produce next month, so this is month 1. So whatever you produce in next month, plus whatever you brought from the last month, which would be how much you produced x1, you sold 500. So whatever left over, okay. This should be greater than equal to 100. Now part 3, you do the same thing. x3 you produced plus whatever you produced last time and the previous time minus 500 minus 100 greater than equal to 2800. Part 4 would be x4 plus x3 plus x2 plus x1 minus 500 minus 100 minus 2800 should be greater than equal to 850. Okay, so this will totally make sense. This is not easy to write, so we make it nicer to write. Okay, so let's make this guy plus s1 equal. Nothing changed. I added that. Now I know that this minus this is equal to s1. So instead of this guy, I would say plus s1. Okay. Now again, I have this. Sorry, this is minus. Now here, this is greater than 100, so minus s2 equal to 100. Okay. Now again, this month, instead of writing down all this stuff, I just bring back s2 here, minus s3 equal to 800, and here you erase all this, it would be plus s3 minus s4 equals to 800. Okay, so I did nothing by just rewriting it in a nicer way. And since you are dealing with a minimization problem, you would never produce more than what is needed. You can always easily change all these guys to be greater than equal. Nothing matters. It's a minimization problem. So you would never, the optimal solution would never be more than what is needed. Now, the only problem left is to write, xi greater than equal to 0. This is important. If you don't write it down, everything would go bad. And the last thing left is to write down the objective function. The objective function would be to minimize the holding cost. You bring so you have S1 unit of inventory here, you have S2 unit of inventory here, S3 here, S4 here. So this would be your inventory. You are paying $15 per unit of inventory. So it would be sigma 15 Si minimize 1 to 4. Done. So the idea is, actually this is it, but that doesn't matter really. Still it would be the same thing, because since the good thing here is that if you make some mistakes in indices, make this 3, 4, make this greater than equal to, since it's a minimization problem, nothing would go wrong. If you even put this S4 here, S4 would turn out to be 0 anyway. So you can just put it sum to 3 or sum to 4, doesn't matter. Now, this would be the writing it down the question. Now the second part was solve it. So there are different ways to solve it. One way is to do the simplex thing, which is really hard. The second way is to guess the solution. and then verify your guess. So we'll see how we will verify our guess. So guessing the solution would be, which you should have thought that guessing the solution is the way, because he would never ask you to solve this problem and things, and that's going to take ages. And 0, 0, 0 is not a feasible solution even. So you have to first find the initial feasible solution, which makes even life harder. So let's see. By guessing, we only have inventory costs. Okay. So the idea would be whenever you don't need inventory, you wouldn't hold it. Okay. So let's look at the last month. In the, let me see. Okay. In the, well, honestly, for this problem, I even don't need this. So let's forget S4. It's not really needed. I don't want to change this thing to equality. I will just keep it like this. I don't care where the thing goes. You can put it there. It's not really important. Let's put it there or not there. Doesn't matter really. Both cases. We can argue both. We can guess in the last month, since everything is going to go finish. We will not carry anything to the next step. Okay? If S4 turns out to be 10, it means that you keep 10 units of inventory without any reason. So in the optimal solution, you can assume that this would be 0. That's why I'm saying that this one can be easily dismissed. So this would be 0. Now the other part is, would S3 would be greater than 0 or not? S3 means that you produce something in the third time and bring it to the fourth time to sell it. So pay inventory over it. But here we would only need 850. And we have the capacity of 1200. So we can already produce whatever we want here and don't carry any inventory. So this would turn out to be 0 too. So we can say that S3 equals to 0 and X4 would be 850. This one we can safely assume because that's basically, we can safely assume this one. Let's put it like this. Now, in the second step, so this guy would also be 0. So we will have X3 plus S2 would be equal to 2800 because you would only produce for this month. You wouldn't take anything to the next month. This guy would turn out to be, okay, let me look at my own calculations. This is correct. Okay, yeah. So, okay. So we are here. Now, X3 plus S2 would be equal to 2800. Now, in each month, you try to produce as much as possible so that you don't bring from the previous one. So you can guess that this guy is at its maximum, which is 1200. And this guy would be whatever that you couldn't produce, you had to produce before to bring it here. Would be 160. 2600. Okay? Now, you go one step back. So you will have X2 plus S1 would equal to this number. Again, you would produce as much as possible here, which would be 1200, and you only bring 500 from the first step. And in the first step, you will have X1 minus 500 would equal to 500. So X1 would equal to 1000. Now, this would be our guess. So I'm guessing that our solution would be writing it down, X star would be 1000, 1200, and 1200, and 850. Now my S star would be for the first period 500, for the second period 1600, and for the last period 0. Okay? S4 I just discarded it. You really don't need it in this problem. Now, and the objective function would be just putting it up there, calculating it. It would be 3500. Now, the second part is, now that we have guessed this guy, how do we verify if it is correct or not? The way to verify it was in the first question. Construct the dual vector. If the dual vector is feasible, you're fine. You have found a set of variables that are both satisfied complementary slackness, dual feasibility, and primal feasibility. So that's the optimal solution. So you just, now, if you're lucky, the dual vector that would make would be feasible in the dual problem, then you're fine. If you're not lucky, that wouldn't be feasible, then your guess was wrong, then you have to solve it in a more manner.
So if the solution is feasible in both
yeah.
primal and
Dual, then yeah, that means it's optimal. That's it, basically. Of course, it should satisfy complementary slackness. Now, for writing it, we have to write down the dual of this problem. So it's U1, U2, U3, U4. Okay? Now, writing them down, it would be maximize 500 U1 plus 100 U2 plus 2800 U3 plus 850 U4. Okay? Subject to U1 plus U2 plus Subject to U1 is less than equal to, it should be like that, yeah. U1 is less than equal, sorry. I have more than one set of variables. I have to put a set of variables for V's too. Let me just make sure that I'm in the correct thing. Yep. So let's see how I design this thing. Yeah, I have a set of constraints. Sorry, I have forgotten those constraints. All of them are less than 1200. I forgot this one. So these all have V1, V2, V3, V4. Okay, so my objective would be this minus 1200 sigma Vi. Okay, so this one I totally forgot, I'm sorry. Now, the next step is U1 is less than U1. To make these all look like this, multiply all of them by a minus and make them greater than equal so that you can easily handle it. So it would be U1 minus V1 should be greater than equal to, should be less than equal to 0. Why U1? U1 is coming from the multiplier of x1 here. There is no x1 here. There is only 1 minus x1 here. So it would be U1 minus V1. And then U1 minus V1 should be less than equal to 0 because there is no x in the objective function. So the multiplier of x here is 0. So U1 minus V1 is less than equal to 0. U2 minus, let's write my v's in a way that are different. Less than equal to 0. U3 minus V3 is less than equal to 0. And U4 minus V4 is less than equal to 0. So this is one set of constraints that you would get. There would be another set of constraints that you would get when you are multiplying for the s's. So it would be minus U1, then S1 is here, plus U2, then S1 doesn't show up anywhere else. It would be less than equal to the multiplier of SY is here 15. Then you have the same thing for minus U2 plus U3 is less than equal to 15, and you will have minus U4, minus U3 plus U4 is less than equal to 15. So you would have three constraints like this too. And you would have all the UI and VI's are greater than equal to 0. So basically what I did, I just wrote down the dual of this problem. Nothing more than what we did in the first step. Now, we have to find a set of UV that satisfies complementary slackness and all this stuff. Let's see what we have. We have that all the x's are strictly positive. So all these constraints are satisfied at equality. So you have U1 equals to V1, U2 equals to V2, we have U3 equals to V3, and we have U4 equals to V4. And then what else do we have? We have this guy and this guy are strictly positive. So this guy and this guy are strict. They are satisfied at equality. So you have U2 minus U1 equals 15, and you have U3 minus U2 equals to 15. What else do we have? We have these constraints, these two. Let me find them. X1 and X1 and X4. These constraints are not satisfied at equality. They are not. They are strict inequalities basically. And when they are strict inequalities, the dual variable for them has to be 0. So V4 and V1 are 0. So this is 0, this is 0. When this is 0, this is 0. This would equal to V2 because of this. And minus 15 equals 15. So V3 equals 30 equals to U3. Okay? So we have U1 equals to V1 equals to 0, U2 equals to V2 equals to 15. We have U3 equals to V3 equals to 30, and U4 equals V4 equals to 0. So we have a U vector and a V vector which are positive. So they are feasible, they satisfy all these constraints, they satisfy complementary slackness. X is also the same thing, so this is optimal. If it was not optimal, for example, this number would have turned out to be minus 30. If it was minus 30, then it wouldn't satisfy this, then you are not at the optimal point. Okay? This would be the, yeah, that's it. This is part A.
In this one, when you wrote the double problem,
Okay.
you changed the sign.
Oh,
Yeah, but you also modified the actual problem by assuming it to be greater than equal to 1. It should be equal to once we have added the...
no, it's the same thing. You could have assumed that this is less than equal to 200, 1200. Then while writing it, the sign, you should have been careful how you are writing
Yeah,
the
I
sign.
mean, the sign has to be flipped if in the original primal problem, the signs are of that same variable in two equations is different.
Yeah. But basically what I did was this. I said instead of saying x1 is less than equal to 1200, because I wanted everything was greater than equal and I was just adding them up, I said instead of this, look at this.
That's okay. My question is that if there is an equality also in between,
Oh, there's an equality in between.
then what do you do?
You don't care, you just write it down. Because an equality, you can write it as both ways. Doesn't
So
matter.
it would be like x1 minus something minus or plus.
Yeah, it's just, you can write down whatever is the thing here. Yeah, it wouldn't matter at all. For writing the dual of a primal, just in your book there is a, chapter, just look at how you write it down. It's not it's a totally mechanical way. It's not something that you need any intuition for it. So this was part A. So we found the optimal. The part B says that assume that the demand is periodic, which means that this is going to repeat next year, and the year after, and the year after. Not modify your problem. So the first step, okay, assume it's okay. It's not okay yet, the second constraint doesn't change. You bring something, you then take it to the next step. Then you bring something to the third quarter and take it to the fourth quarter. Here in the fourth quarter, we didn't take anything to the fifth quarter, which is the quarter after this. So we have to plus minus S4. This time S4 would have a meaning. Now you have to write down the equation for the next quarter. But the constraint for the next quarter is just the constraint for the first quarter. And you can, if you think logically, this problem would have a solution which would be repeated every year. It wouldn't have a solution that would change over the year. Your demands are constant over the year. So it wouldn't make sense that it would change over the year. So whatever happens is that whatever you have extra here, you just bring it here. So here, this is in fact, you're making an assumption. The assumption you're making is that in the optimal solution, at the end of each year, you would have the same amount of inventory that you had at the end of the previous year, which is a logical assumption because this is just something which is repeating. So making that assumption, then you can say that this is the inventory from last year, which would be equal to the inventory from this year. Or if you don't feel satisfied with that, put this S0, and then you have to add S0 equals to S4, which would result in the same thing. Because you cannot write down this infinite number of equations. Doesn't make any sense. And that would be part 2. This would have been the hardest question of this exam. So I think it took us even more than any other thing for 35. Now, the next question, hey, ask me questions if any part doesn't make sense, okay? I'm going to be going fast. The next part is a little bit mechanical. You had to do some calculations that you didn't have to do that much in the previous step. That's right.
1.5 page.
Huh?
1.5 page.
Yeah, not 1.5 page really, but okay. Maybe 1.5 page. Yeah, but this one had, but you should feel comfortable with doing calculations.
That's not right.
Okay, because after all, you have to do some calculations, Not everything should be. So let's see what's the calculation part here. And this one you nearly had the solution in your lecture notes. You just had to plug in the numbers in the solution. So you have identified the gold mining stock, attractive, good company, blah blah blah. Okay, the share is $100 per share. The stock is sold at this thing. Now, And 1 month from now, the price would change. And we have a probability distribution for the price. So this would call it scenario, this would call it probability, and this will call it price. So in scenario 1, with probability 5%, let me write it percentage-wise, it's easier. The price would be 150. In scenario 2, with probability 10%, the price would be 130. In scenario 3, with probability 20%, the price would be 110. In scenario 4, with probability 30%, the price would be 100. In scenario 5, with probability 20%, the price would be 90. And in scenario 6, with probability 10%, it would be 80. And in scenario 7, with probability 5%, it would be 70. Now we want also, okay, so we want to hedge this investment by using put option. So what's a put option? The right to sell. So basically, the put option would, okay, let's look at the options, and then I think I can explain in numbers much easier than anything else. So, option A, B, C, strike price, option price, 90, 100, 110, 2.2, 6.4, 12.50. So basically, if you buy, for example, option A, with a strike price of 90, it means that you have the right that somebody guarantees that if you want, 1 month from now, he would buy from you one share from this company at this price, whatever the price is in the outside market. So if for some reason the price in the outside market goes to 0, it's an extreme case, then you can just go and get whatever zeros you want and sell it to this guy, because this guy has guaranteed that he would buy it from you. So that would be a put option. It's the other way around. It's called call option. You have the right to buy. Okay. Now, so obviously, whenever the price goes up, the option would be more expensive too. So if you want to buy a $110 option, meaning that you have the right to sell, the guy would definitely buy you at this price, but you have to buy this option at this price. You have to pay this amount to this guy now, and he would guarantee that next month he would buy it from you if you want. Now, the question is, you want to purchase X dollars of a stock of this company, Y A dollar of type A, Y B dollar of type B, and Y C dollar of type C. And to make it just to normalize everything, we assume this thing. So it will be the percentage of your money that you want to put. A percentage of your money you want to buy stock. A percentage you want to buy option part A, option part B, option type C. Now the question is, what is your return in the 7 scenarios? Okay, this is totally mechanical. So you have to draw a picture. Scenario 1. Let's call it, well, probability. I'm going to write the probabilities here. So which happens with 5% probability. Then we will have stock A, B, C. So let's see what happens. So if scenario A happens with probability 5%, you have bought the stock at $100. Now stock is $150. So how much money you have made? $50. With the convention that you have here, 0.5. Okay, he's writing everything in $100.
But I wrote it in $50, and then but isn't it X over 100 times 150? Because you bought X.
Sorry. Yeah, that's right. Sorry. So that's why I got the number. Sorry. So what you have, you bought it for $100. Okay. You made $150. So it would be $50. How much you invested? $100. So it would be half. So if you spend $1, you will make 50 cents profit.
If I don't write it in
percentage, so your revenue would be 150, your profit would be 50.
If I don't write it in percentage terms, then
you cannot write. What do you write then, for example?
So
50.
50 is my profit from that stock. 50 is a profit.
50. Okay, if you write 50, then you're assuming that you are
Investing 100.
investing
Yeah.
$100. I think your object, I think your solution shouldn't change.
Yeah, it should.
It shouldn't change because it's just scaling it by number. But let's write that. It's just the same.
Yeah,
It doesn't matter. So this is so if you buy the stock, you will make this amount of money. If you buy option A, you have the right to sell at this price, but you have to go and buy it at this price. So you wouldn't exercise. You wouldn't do it. So basically, you would lose all the money that you invested. So you paid, if you bought one unit of this, for example, it would be minus. You made $0. You paid this amount, and this was the amount of your investment. So it would be minus 1. Okay. So minus 1. And the same goes for B and C, because all of them have the strike prices lower than the current market price. Now in case 2, which happens at 10% of the times, let's see what happens. Stock is $130 now, so you are making $130 on something that you invested $100, so it would give you 0.3.
What? Quick question.
Yes.
Wouldn't your total return though, like, because that just gives you the return of each individual part.
Yeah.
Your total return though is going to be like x over 100 times 150 minus 1 over 1, right? Because you invested $10.
No. Think of it like this. If you invested $1, you will get this amount. If you invest X dollar, you will get X multiplied by this amount, which would be the same thing.
But I'm thinking of the return for the entire, like, the total return for period 1, right?
Yeah.
You invested 1 total because x plus y plus
Yeah.
y, they have to equal 1, right?
That's right.
So the total amount you made is going to be the amount of x you have, which is x over 100 times 150 because that's what it's worth, minus the amount.
You're saying if I invested X dollars
Right.
in a stock,
Yeah.
Right.
So that would mean that how many shares? Shares would be X over 100.
X over 100,
Right. So you multiply that by 150 because that's the new price. So
That's
that's
right.
what you have.
yes.
What you invested was 1, so you subtract 1 because x.
No. You didn't invest one.
But it said that x.
Yeah. But now you have a part of it invested for this X, a part of it you invested in this, a part of it. So it would be minus X. This is the amount that you.
No, but x is the actual number of dollars that you invested. Or
I'm
X-
buying a stock. X is the amount of dollar you use to buy a stock.
Right.
Y is the amount of dollar you use to buy.
Right.
So
And then the problem says that x plus ya plus yb plus yc is equal to 1.
That's right.
So the total amount that you invested is 1.
Yes.
The total amount that you made is x over 100 times 150. So it's going to be x.
no. You make some. Oh, in this case you're saying in case 1.
Yeah, in case.
Oh, okay. I got it. Okay. That's right. Minus 1.
Yes. Okay.
Okay. Yeah, that's right. Well, the way I would have written it down is minus X divided by X. Okay.
But it-
Then plus Y divided
Right.
by
But
X.
they're all
And then you would use the fact that they add up to 1. It would be the same thing.
Okay.
You're right. So now, in the scenario 2, all these guys, the strike prices are lower than the market price, so you wouldn't exercise your right. You wouldn't go and sell at these prices because it's already cheap. So minus 1. But your stock would be this amount, 0.3. And each dollar you would make 30 cents. In scenario 3, which happens 20% of the times, now exercising C would be indifferent. You would buy and sell at the same price. So let's say you lose your money still, and well, basically you lose your money because of it. You exercise it, 110 minus 12.5 divided by minus 12.5. So this would be 0 cents. So all these cases you would lose money, but your share would be 110 minus this would be 1, so it would be 0.1. In case 4, which happens in 30% of the time, now there is some difference. A and B would still be negative because you wouldn't exercise it. But C you would exercise it. And you're going to go and buy 1 unit at $100 from the market, sell it at 110 to this poor guy, and also you have already paid this amount for it, divided by 12.5. This is the amount that you get. This turns out to be plus 10, divided, this would be minus 2.5 divided by 12.5. So you're still using money, but it's less than if you don't exercise your right, you're going to lose all the money. But here you're going to use a fraction of your money. So it will be minus 2.5 divided by 12.5. Okay? Now,
Could you explain that once again?
yeah. So what happened was the price was 100 in market, but you have the right to sell to somebody at 110. So you're going to sell. So you go and sell at 110, but you have to pay 200 to buy it. So you make $10 here. You have already paid 12.5 last period to just buy the option. So you have paid minus 2.5 and you have invested this amount. So this would be your return. For the stock, your return would be 0 because the price didn't change. Now, in scenario 5, which happens in 20% of the times, now you're going to exercise B, and you're going to exercise C both of them. So C would be 110 minus $90 minus 12.5 divided by 12.5, which would give you 20 minus 12.5 is 7.5 divided by 12.5. So it's 7.5 divided by 12.5, which is wrong in your solutions here. I'm going to correct it. It's 8.5 in what you have there now. And for B, you would also exercise it. So it would be $110, you sell it at market, 100 is the price that you sell in there. Because of this, you buy from market at 190, and 6.4 is the value that you paid for Getty for buying this option, dividing it by 6.4. This would be 10. 10 minus 6.4 is 3.6 divided by 6.4, if I'm not mistaken. You're right. 3.6 divided by 6.4. A, you still are not going to exercise it, and on your stock that you bought, you're losing money. How much? 90 minus 100 divided by 100, which makes it minus 0.1. Okay. Now, 6 and 7, the calculations are exactly the same. So I'm not going to write them down here, but you can do it easily. So on the stock you would lose minus 2. On your stock once you would lose 80 minus this, once you would lose 70 because the price is going down and down. So this would be this. At $80, you're going to exercise option A. So it would be 90 minus 80 minus 2.2 divided by 2.2. This would give you 10. 10 is 7.8 divided by 2.2. So it's 7.8 divided by 2.2. Now you can easily find the pattern on how these numbers go up. Each time $10 is added to it. So it's 13.6 divided by 6.4. Why $10? Because the price is going down $10, so you're always making money, $10 more $1. 20.6 divided by 6.4, 17.8 divided by 2.2, 17.5 divided by 12.5, and 27.5 divided by 12.5. So these would be your returns. And so if you spend, for example, X some dollar on, I don't know, a stock, and scenario 4 happens, you're going to make $0. Now, the question is asking you, what's the, okay, this was one step of the question. What are the payoffs in different scenarios? And what's the expected payoff? So to find the expected payoff, you have to multiply each case by its probability. Okay? So we call this matrix A transpose. And so this matrix is called A transpose. Let's call it A transpose. Now, if you go and invest Z, which we call it X, YA, YB, YC, we want to see that in each of these scenarios how much is your payoff. So A multiplied by Z would be your payoff matrix. What's A? This is A transpose. So A would be 0.5 minus 1 minus 1 minus 1. So 0.5 multiplied by X minus 1 multiplied by A minus 1 multiplied by B minus 1 multiplied by B would give you the payoff in total if case 1 happens. So AZ, which would be a vector of 7 elements, so 1 to 7, each element will give you the payoff in scenario A, scenario 1, 2, 3, Okay.
A transpose or
A transpose, I call this guy A transpose. So A transpose is a 4 by 7 matrix. So A would be a matrix with 7 columns and 7 rows and 4 columns. So let's write it down the first 2 rows. -1, -1, -1. 0.3, -1, -1, -1. This would be A. And this is going to be replicated. And you will have X, YA, YB, YC. So when you multiply, the first column will be this, the first element will be this multiplied by this. The second will be this multiplied by this. Each of them will give you the payoff in one scenario. So when you get AZ matrix, this would be the payoff in each different scenario. Now you define a P vector, which will be a vector of probabilities. 5%, 10%, till 5%. Now you need to multiply this by this, multiply this by this, and add them together. This would be P transpose AZ. It's a column. You make it a row vector, you multiply it by this. So P transpose AZ would be your expected payoff. And I don't think you were required to calculate it. Or were you? No, you were not required to calculate. So P transpose AZ would be your expected payoff. Now, the next part of the question was asking you formulate a linear program to maximize the expected return, subject to the constraint that the return in no scenario is less than minus 2.5.
Question.
Yes.
Instead of doing this way, can we find the expected stock price by multiplying the stock and times the probability, and then finding out which options are in the money, and then finding out the payoff in one step rather than doing this?
So you mean, so what should I do? You just
You know
walk
the
me through
expected
it.
stock price, which is 5% times 150 plus 10%.
Okay, I find the expected price, okay?
And then you know which other options are in the money based on that expected stock price.
So you want to take the, I think that, so my expected price would be something like, have you calculated it? So let's say it's, I don't know, 120,
Yeah.
something. Then what will you do?
Then I will see if A, B, C are in the money. If they're in the money, then I'll calculate the payoff. Otherwise, no.
And then you have to find the probability. I think you have to work out more details in that. It's not that straightforward, but it should be possible.
Because all these will end up.
Yeah, this should be possible to do it, but you should just be careful to write down the probabilities correctly. Because how do you know that when you're going to get the money for, let's say it turns out to be 100. So you're just going to go that this will never be exercised and this will always be exercised?
Yes.
I'm not sure that's going to work. No, I don't think so. You might be able to do it using this number, but I'm not sure that if you do it just directly like that this is always exercised and this is never exercised. I don't think that's going to work. I'm not sure.
Because is this a path dependent or path independent?
What I did? Well, yeah, it depends on what happened in the past, yeah. With just one step behind. I don't think that will work. I'm not sure. I don't think so. I'm nearly sure that it will.
Okay.
Can you just write down what your, like, given that interpretation of the problem, what your total return would be in scenario 1? I'm just a little bit...
Yeah, the total return in scenario 1 would be what I have right there. It would be 0.5x
It's not the same thing.
minus YA minus YB minus YC. It would be the total return in part A. If A happens, and you have invested X in a stock, YA in option A, YA. This is the total return. Now, to find the linear program that would maximize the expected return, so this really doesn't need that much space. Maximize the expected return. What's the expected return? What does he call it here? Okay. The expected return, let's see, just a second. Okay, no, that's a second. So I'm trying to maximize P transpose AZ, which this one I call it C there. That's not really good. So maximize P transpose AZ, which is maximize the expectation, given that in each scenario payoff was given by elements of AZ. So elements of AZ, all of them should be strictly greater, should be greater than or equal to minus 0.02.5. We can delete that 1 which is in the solution. You really don't need it. So basically I'm saying that minus. Yeah, so, and also
Scenario 1 is
1 transpose Z, which means adding them up equals to 1. Okay. But you can have Z negative. You can short that also. So what you have is, you're saying that maximize the expected profit, which is what I calculated right now. Given that in each scenario, it means that each element of this would never have a payoff less than this amount, and also they add up to 1. It means that I spend all my money. Okay? Now, the second part says, instead of doing this is very strict. Do this that the probability that the return would be less than minus 0.025 is less than 15%. This one is saying that the return is never less than 15%. This one is saying that, okay, instead of doing that, just I'm satisfied with if you give me a solution that says that this one would never have a return less than this with the probability higher than 15%. Okay? Let's see how do we do that. For doing that, we have, the only thing that we have to do is to look at all the cases here. Look at just, look at the cases that they add up less than 75, less than 15%. It means that the probability of them happening is more than 75%. Okay?
The last two would be lower, right? 6 and 7.
Well, no. I'm just adding them up. For example, 1, 2, 3. Let me write it down and then explain. I think that would be easier. If I give you a portfolio that I tell you I'm sure that in cases 1, 2, 3, 4, 5, and 6, it will have a return more than that amount that I want, then I'm sure that only in 5% of the times I will have a return less than that. So I have to take all the combinations that their probability is more than 85%, and make sure that in those combinations I make more than that money. So for doing that, I look at it like this. I look at the events that when I add up the probability for them, the probability of S1 would be less than or equal to 15%. So 1 and 7 is 5% and 5%, probability of this one is 10%. Okay? Then if I write down all those guys that their probability is less than 10%, it's these events. Okay, so these are the events. 1, 2 would be 15%, 1, 6 would be 15%. So these are the events that probability of them happening is less than 15%. And it's all the events that probability of them happening is less than 15%. Of course, I didn't look at the events like only 1 or only 7. They would be already embedded in this one. Now, what I do, so the complement of these guys are the guys that the probability of them happening is more than 85%. So this would be 1, 2, 3, 4, 5 cases. So if I make sure that I give you a portfolio that in these 5 cases, but in the complement of these 5 cases, makes more than 25%, then I'm 100%. Then I'm sure that in more than 85% of the time, I would make more than this amount. Or in other words, in less than 15% of the time, I would make less than this amount.
Could you repeat this?
Yeah, okay, it's a little bit confusing, yeah. Hey, if I give you a portfolio that I assure you that in cases if 2, 3, 4, 5, or 6 happen, any of these happen, you would make more than this amount. So if these happen, you will make more than this amount. What's the probability that you will make less than this amount? It's only if these two happen. But the probability of these two happen is 10%. Which means this, probability of a revenue less than this amount is less than 15%. So I have to look at all these cases that the probability of their complement is more than 85%, and make sure that in their complement I would have enough revenue more than this amount.
But how did you come with this initial premise that 2, 3, 4, 5, 6 have?
Oh, you just have to look at these numbers. So I wrote down all those that have probability happening less than 15%. So 1 and 2 But 1 and 3 is not there because it's in 25% of the time this will happen. 1 to 1, 6 and 1, 7. 1 to 1, 6, 1, 7. Then you go to 2, 7. 3 with nothing, 4 with nothing, 5 with nothing, 6 and 7. These are all those add up less than 15.
So you don't really have to take the, like, 6 on its own or 2 on
Okay,
its own.
if I make sure that if 2, 3, 4, 5, 6 happen, I would make more than this, then even if I also, so let's put it
You're
like
only
this.
gonna make more.
If I give you a portfolio
Gotcha.
which would make more than this if only this happens, it would be a better portfolio that if I want to also make sure that in case 7 it would also make more than this. This is putting more restrictions. So I would just give this one and that's enough. That would be even a better portfolio, but you don't want it really. It would be much nearer to, I forget. So it's just that you don't need to worry. Now, you have to write it down like this. You, for example, 1, 7. Okay, look at 1, 7. I go and delete this guy and this guy. So now this would be the return in case 2, 3, 4, 5, 6 happen. Okay? Yes or no?
Yes.
Yes. So I call this, if I call this S1, I call this A1 transpose. Okay? I write down exactly the same thing. Maximize P transpose A1Z, given that A1Z is greater than minus 0.25, and I have 1 transpose Z equals to 1. So what does this program does? This gives you the best return conditioned on in cases 2, 3, 4, 5, 6, you make more than that amount. So you have to write down, sorry, this is 2.5. So you have to write down A1, A2, A3, A4, A5. So you will have 5 different LPs. You solve them. That's all. That's it.
So what's going to be the
I
final
was going to say,
solution?
did a single person get this one right?
Yeah.
Oh, yeah.
You might get it straight.
I haven't, honestly, I haven't.
I think
this one.
one LP is enough.
Now that I think of it, this is a little bit hard.
Out of the 5 solutions, which one is?
Each of them is correct. Yeah, because each of them would give you that portrait. Or just a second, you can do something else. All of them. So you will have Z star 1, Z star 2 to Z star 5. These would be solutions for each of these cases. Each of them is a different portfolio with different return, but all of them guarantee that the probability of this thing happening is less than 15%. Look which one of these 5 gives you the most amount of return, pick that one. But if you're not really interested in maximizing it, you're just interested in this guy, you pick any of them. But the rational thing would be, okay, look at these 5, compare them. Whichever one is better, take that. Yes?
Because in if we insist that in the scenario return is greater than negative 0.2, then in the scenario 1 and 2 will never.
You don't care what happens in scenario 1 or 2, but you are sure that scenario 1 and 2, 1 and 7 only happen in 10% of the time. So even if you are getting the worst possible payoff, minus infinity, this minus infinity would happen in less than 15% of the time, and that's what you're worrying about.
Because if we put the scenario 3 in the constraint, then 1 or 2 will never be less than.
Yeah, exactly. So we don't look at the case that in this none of them is 3 is not here.
Yeah. So the A5 will be the best.
Sorry?
Because
if 3 is there,
yeah, so the 1 or 2 will never be, the return of the 1 and 2 will never less than the, because the return 1 and 2.
I see. Oh, you're saying that these 2 are always better than
Yeah,
this.
right.
Okay. Yeah.
So I think.
Yeah, if you put 3 there, then the solution for 1 and 2 is always better than the solution for 3.
Yeah, so.
But because the probability of happening 3 is really high, you don't want to take the risk of that.
Yeah, right.
Because if you put anything in 3, then there is a small probability that if you put all your money here, then you will make a big loss. But here you are making sure that even if you're making sure that in case, for example, in the first one, 1, 7, I'm making sure that if 2, 3, 4, or 5, or 6 happen, then I would make more than that amount. And what's the probability of these guys happen? 90%. So I made sure that in 90% of the times, I'm going to make a minimum guaranteed amount. In 10%, you are not guaranteed anything. So basically it's saying that, okay, if you have this portfolio, and you assume everything fixes the same, you always buy this thing. 90% of the time, you're going to make more than this amount. 10% of the time, you're going to make less. That's all I'm saying.
I mean, not 10% when less, because the first return always greater than the scenario 2. And
yes.
So if we insist the scenario 3 is on the constraint, so
but if you okay. Assume that you make sure in scenario 1, 2.
No. We first of all we do not to consider which one should be in the
constraint.
Yeah. So,
okay.
So we can find that the 3, 4, 5 should be in the constraint, right?
Okay.
Then because if the portfolio if any portfolio make the scenario 3 if the return of in the scenario 3 is greater than my constraint, our constraint, then in the scenario 1 and 2 will be.
You're saying that if I guarantee that in scenario 3 I make more than this, then I'm already guaranteed in 1 and 2 I would make more than this.
So we don't care 1 and 2. We just 3, 4, 5 enough.
Oh, you're saying that if I just make sure that in these 3 cases I make enough amount of money, then it would. I'm already guaranteed that in all these cases.
Yeah, right.
Okay, let me see.
So
but you wouldn't lose anything. That would be again another. It wouldn't help you in solving the problem. You're right. It might make one of your problems easier, in a sense that the number of constraints instead of being 10, it would be 7. But still, you have to solve these 5 problems. I see your point. It's like that. Here, I'm saying that I'm going to make sure in the first case that in case 2, 3, 4, 5, 6, I make enough money. But you're saying you don't need even to put 2 there. Just say that you want to make sure if case 3, 4, 5, 6, you're going to make enough amount of money.
But I think that the solution of the A5 is the best because the constraint of the.
Oh, I see. Let me just make.
Yeah, the field area of the A5 is the biggest.
Ah.
So I think the one LP is done.
Let's talk about it after the class. I'm not sure about that yet. I have to think about it.
Okay.
But I don't think that would help you. It might just make you solve some of these easier, but it wouldn't reduce the number of problems that you have. But let me think about it and we'll talk about it. I really don't. I never thought about it.
Because the field area of the A5 is the biggest. Also, in the A5, we guarantee another 4.
I see your point. I really don't know. I should think about it. I'll let you know. Something that I never thought of. Okay, where was I? Now, okay, this is done too. Let's see. This took us a long time. 5, 10. Now there are 2 questions left. The last question is very easy. So, in fact, I'm not even worried if I spend 45 minutes on the 4th question. The last question was really easy. I hope that you got to it when you were doing the exam. Now, probability and sensitivity analysis. Okay, so we have some guy pottery who produced 4 type of china, blah blah blah. So it had resources. The resources were these are the products. P1, P2, P, and these are the resources. The resources are clay, enamel, dry room, kiln, and this is the profit. and E is English dinner set. It uses 10 pounds of this, 1 pound of this, 3 hours of this, 2 hours of this, and this is the profit. 15, 2, 1, 4, 100, 402, 10, 2, 6, 2, 66, 10, 1, 6, 5, 66, 21, 3, 3, 89. And then I have the maximum amount that I can use on each of them. Okay? And we also, there are some constraints. So these are different sets. English, career, I don't know, different names. And P1 and P2 sets should be produced at the same amount for some reason. Somebody told me. And then, so you have to write an LP to solve this, to find the maximum profit. So it's a very easy LP, maximize. In fact, you even didn't have to write it because it was written for you. 51, what did you, A, plus 102C, plus 66 P1, plus 66 P2, and then I will write one of the constraints only, 10E plus 15C plus 10 P1 plus 10 P2 plus 20 B, 59B. B is less than equal to 130, less than equal to 30, less than equal to 45, less than equal to 23, and everything is greater than equal to 0. And there's also P1 minus P2 equals 3. So this will be a program, solve it, done. Now, the sensitivity analysis results are given. I don't write the table, we will just use the ones actually. Now, let's see, it's a good exercise to see what you need. What's the change in revenue if the price of blue tail increases to 92? So the price, which was here, if it increases to 92, what's the change in revenue? So we have to look at the sensitivity analysis for the coefficients of the objective value, of the objective function. The objective function for, so that line for B says objective value is 5. It means that you're going to produce 5 units of this. The objective coefficient is 89. Allowable increase is 47. Allowable decrease is 12.5. So it's telling you that you can increase this coefficient by 47, make it 136, and still you will produce 5 units of this in the objective. So we are just increasing it by 3. So we know that the objective, the optimal result, even in that case, wouldn't change. Only the value would change by 3 units, by 3 times $3 multiplied by 5 units, $15. You're going to make $15 more. Now, should the manufacturer buy an additional 20 pounds of clay at $1.1 per pound? So we look at the constraint for clay. Now, it's telling you, should he go and buy and make this 130, 150 and pay $1.1 per pound for each of these? You look at the dual variable for 130. The dual variable for 130 is given to
1.42.
Exactly. So that clay line will be, the dual variable is 1.429. This is the right-hand side value, 130. Increase is 23.33. Allowable decrease is 43.75. Okay? So we are increasing it by 20. It's in the range that you can increase. So basically, if you increase it by 1 unit, you will make this amount of money. But you also have to pay this amount of money. Since you have to pay less than the amount that you will make, it's good to do it. So 1.429 minus 1.1 would be the profit that you would make on increasing it by 1 unit. You're increasing it by 20 units, and since it's in the allowable increase range, you can use this number. This would turn out to be 6.58. So you would better increase it, and you're going to make this amount of money. Now, suppose the number of hours available in dry room decreases by 30. So let's look at this number. 45. Now it's going to become 15. Okay? We look at the sensitivity analysis row for this. It will be dry room. Dual variable is 0. It means that increasing it wouldn't have any value. Its value currently is 45. And although the increase is plus infinity, just take it to plus infinity, nothing will change. For example, this is satisfied, let's say, at 30 less than 45. Make it infinity, nothing will change. And although the decrease is 28. So you can decrease it by 28 and nothing will change. So you can guess, and it's not a guess, it's in fact, that 45 minus 28 would be how much? 17. So basically this is satisfied at something like this, 17 less than equal. But now you want to make it 15. 15 is not a feasible thing. It's not in this range. So you cannot use these numbers. Now, so basically the question is not asking you to give the exact value, but it's just asking you to give the a range on the amount that your profit would decrease. Obviously, 0 is the upper bound. Well, doesn't matter. Your profit currently is X. Okay. Now the new profit would be, let's call it X star. The new X. The new profit would be X prime. Okay. X prime we should give a upper bound and lower bound based on X on it. You can easily say that it's less than X minus 0. It wouldn't increase your profit if you did. You just have to find the lower bound on it. Okay. Now, to find the lower bound, there are different ways. Well, this is a nice one that you see here. And depending on the time of the problem, it might be a good or bad one. You might have come up with your own bounds. I have to look at the question and see what find it. But one bound that you can come up with, this is a good problem that if X is feasible in it, X as a set of solutions, any number less than that would also be solution. Just you need to satisfy this one. Because all the constraints are less than equal. So if you make them even less, the feasibility would remain. So as long as you make sure that you produce equal amount of these two, everything would remain the same. Now, we know that X star, which was the optimal solution of that, was something. But we can also say that 15 divided by 17 X star is also a feasible solution. Why? Because whatever you're producing of these two, again you would be producing equal, and all these guys would be satisfied. But then, 15 X star divided by 17, this guy would also be satisfied. So this would be a feasible solution to our original problem. It's not the optimal solution, but it's a feasible solution. Okay? But we know that in that feasible solution, this would be satisfied at 15 less than 45. So then that feasible solution would also be feasible for this problem. Yes?
This might be a little trivial, but like, I mean, it's not going to give as good a lower bound as that one. But like, you could look at the fact that of the two things you are producing, because remember there's only two things you're producing in the optimal solution. You're producing C and I forget what else you were producing.
B. C and B.
Right, and you're producing 2 units of C, right?
Yes.
So each unit of C took 1 unit of dry kiln and it had the highest profit. So I figured, okay, if you just decide, okay, those 2 hours that you're losing, you take away the 2 C's because...
And then you have a lower bound, yeah.
Right, so I mean, but is that...
That's a lower bound. It's not a good lower bound, but we should check it. Maybe it's even better than mine. I think
it's not.
It's not better, it's not better. But that's a lower bound too. So you might have come up with lower bounds and upper bounds which are... Okay, if your lower bound is very bad, okay, you wouldn't get all the points, but you would get points, don't worry. Because it's just the idea of coming with it. Yeah. So I said that, I know that X star is a feasible solution here. I'm going to argue that 15 over 17 X star is also feasible. Why? Because all of these are less than equal. I'm decreasing these sides, so they are feasible. And also this one is also feasible because whatever was producing here and here, both of them are just divided by 7. So this equality is also the same. So this is a feasible solution for this problem. Now I'm going to argue this is our problem. But I'm going to argue this is still even a feasible solution for this problem when you are decreasing it. Why? Because before changing anything, this guy was satisfied that this equality was like this inequality. So it was like this. There were some numbers, a1, x1 plus a2, x2 plus a3, x3 equals to 17, which was less than or equal to 45. Now I replace all these guys by 15 divided by 17. Because each of these x's individually were replaced by that. So this is also becomes 17 multiplied by 15 over 17, which equals to 15. Okay? Yes or no? Okay. So, that's okay? So I'm just saying that now, this, even if I decrease this 45 to 15, this new solution is still a feasible solution. Okay? But we know that any feasible solution is a lower bound for the optimal solution. Optimal solution is the best of the feasible solution. So just, and multiplying this number by 15 over 17, what would be the optimal profit here? Just multiply whatever is the optimal value by 15 over 17. So which would give you, I don't have the number here really, but it would give you 547 minus 6435. It will give you this value. So basically this is the Z star that's going. This was the original value minus whatever it costs. So basically what I did, I just calculated the objective value instead of at X star at 15 over 17 X star. And which would be 15 over 17, 547. Okay, this is the base of the right. So since I know that this is a feasible solution for the new problem, which is everything less than 15, okay, so this value would be a lower bound to the optimal value of the new solution. So this would be a lower bound, which is 547 upper bound. It wouldn't go above that, and it wouldn't also go below that. So the new solution would be in this range.
Two questions. One, why 15 by 17?
Because I knew that this is, before changing anything, we had 17 less than 45 here. And we know that we are changing this 17 to 15. So we wanted this number to be less than or equal to 15. So we decided to multiply it by 15 over 17, so that the 17 with 17 will cancel out, and we have 15.
And how does it ensure even?
Huh?
How does it ensure even?
Oh, because whatever I was producing, so what's this? This is, in fact I'm saying your new solution is this. P,
Then you're not changing any independent quantity.
Yeah, we are just saying, so whatever you're producing of this, now produce this ratio of it. So since these two were equal beforehand, now you are just going to produce the same ratio of the same equal. Okay? Part D is saying, what is the minimum price at which it will be profitable to produce primrose? Which is these two guys, P1 and P2. So now let's look at it. This is a little bit tricky. Let's see what's the cost of producing these two. So how do you find out what's the cost of producing these two? Assume that you have everything and you want to produce these two. You look at the dual variable for the right hand side. The dual variables are this. 1.429, 0, 0, 2, 20.143. So basically if you want to start producing these guys, these two you have them already. Let's think of it like this. But these two you have to go and buy at these prices and start producing them. Okay? Now, so it would be P1, we need 10 units of clay, 2 units of film. So it would be 10 multiplied by 1.429 plus 2 multiplied by 20.143. Okay? So this would be 54.573. So this would be the price of producing 1 unit of this. Now, price of producing 1 unit of P2, this is P1. P2 would be 10 units of 1.429 plus 5 units of 20.143, which would give you 15.005. So this would be the price of producing 1 unit of this. Price of it. You don't need to buy any new of these two because basically we already have extra, but these two you have to use it all. Now these would be the prices, but we know that we have to produce equal amount of those. So basically the price would be the average of these two prices, because you have to, if you make 1 unit of this, you also have to make 1 unit of this. So the average of these two prices 54 plus 1/15 divided by 2 would be 84.79. So, if you can sell 1 unit of Primrose at this price, it's better to go and produce it. Yes?
This might be, I mean, I'm guessing it gives you the same answer, but like I didn't think about it at the time of the test. But like, if you have, it also gives you in the in the sheet, it tells you the allowable increase for the objective coefficient of P1 and P2.
Okay.
It's 37.571.
Yeah.
At the time, I thought, okay, it would just you could increase it by 37.571.
And then they become...
And it becomes profitable. But I guess because there's two of them, if you divide it by 2.
You can, I think you can use data to get this, but I'm not sure how. I have to write it
Well,
down.
because it would just be 37.571 divided by 2 plus the 66 gives you the same answer.
Gives you the same answer?
Yeah.
66. Where did you get the 66?
Because
Yeah,
66 is
that's
the
correct.
original.
That's correct.
Right.
So, what was the idea that he was saying? He was saying that if you can, instead of that, you can look at the report for the coefficient. It says that the coefficient, this guy is 766, and its allowable increase is 37. We know that this value is already 0. What does this mean? This means that if you increase this by 1, 2, 3, 10 units, this would remain 0. But if you increase it by 37, it would not remain 0 anymore. It would become positive. So it means that if the price goes above that, it would be profitable not to produce something and start producing this kind. This number is the same number as the one here. That's totally true. Correct.
Unfortunately, the 30, I just said it was 37.571.
I'm not, just a second. Is it the same number if you divide this by 2?
Yeah, if you divide that, if you
By
divide the
2?
37.571 by 2, it's
By
because
2.
each.
No, this is the same number. I'm not sure. Did you check it with your...
Yeah, it
check
ends up being 84.7.
That's totally right. Yeah.
Because
Because you have to make 2. Because when you have to increase it, these two would always have the same coefficient. Why? Because they are the same product. They have different methods of production for you, but you're going to sell them at one price in the market. So you cannot increase just this guy and keep this guy. So you're really increasing both of them. That's why you have to do
actually,
it. It should be correct. No?
no, that's
So that line of reasoning might have been a little bit harder because you have to just
actually no, because you could keep one of them at 66 and increase the other all the way up to 113 or whatever, and then it would still produce even if.
Yeah, but I'm just saying you can. Theoretically, you can do it. But in your setting of the problem, these two would always change together.
Right.
That's the thing I'm saying. So it's a little bit harder to reason that way, but it's correct. Just make sure the number, let me just make sure, it could be 15, 3.18.
I made the same mistake. I mean,
If you increase one of these up by
84. That's right.
So you're saying-
you're going to increase.
yeah, I said that I made the same mistake, but I still don't understand why I should.
What mistake? The mistake.
There was 66 plus 37.
So look, that's the reason that it's, in fact, you're changing two codes. You should, to argue that way, you should be able to argue how your objective value would change if you change two coefficients at the same time. We never studied that. We don't know how to do it. But because of the special structure of this problem, if you increase this by 2, it would be just equal to say that divide this by half and add it. But it's a very, because this is just a special structure of this problem. Remember, all these sensitivity analysis things were valid when you were changing only one value and everything was constant.
Yeah.
But here, if the price of Primrose goes up, it doesn't mean that only one of these goes up. Both of them go up.
Your method was slightly different. How so? How exactly?
Oh, but what I said was like, look at the dual variables. Basically, I'm in a sense calculating forget that. I just look at the dual variables. And I said I have extra of these two, but these two I have to go and buy, basically, to start producing Primrose. So let's see how much I should pay for 1 unit of it. So if I want to use P1, I have to use 10 units of clay, 2 units of clay, which would be 10 units, this price, 2 units, this price. I have to pay this amount to produce P1. But if I'm going to produce 1 unit of this, I'm going to produce also 1 unit of P2. So I also have to produce this amount. So, but the profit, the amount that I'm going to sell it, if it's equal to the average of this guy, it would be 0. It would be, I would make nothing. No roots, no makeup. So if you take average of this will be the average cost for producing. So if you make the price is slightly higher than this, it's worth producing.
The average amount is
This is the cost of producing P1. This is the cost of producing P2. So what's the average cost? Because we have to produce them equal amounts. So the average cost will be this process divided by 2. So if you go and sell 2 units of Primrose, which definitely one of them is P1, the other one is P2, on average each of them have cost you this amount. So if you can sell it at more than this, then you're going to make money. And the last question is not a hard question. The last question is exactly talking about this equality constraint. Says that instead of this, assume this is greater than or equal to 0. In the reformulated problem, would the number of Primrose by method 1 be positive or negative? So basically it's telling you, if you make this thing greater than or equal to 0, is it going to be positive or would this thing become active? Would this equality still hold or no? It will start producing one of them without producing the other one. And you just need to look at the dual variable for this, which is, if I find it,
It's 11 point something.
yeah. So if you look at the dual variable for the Primrose, which is, oh, I haven't written it down here. So the dual variable for this constraint would be 11.429. So basically it means that if it is greater than equal, then it would increase. Because it's worth increasing it. The dual variable is positive, meaning that if you increase right hand side by 1 unit, meaning that if you produce 1 unit of this more than 1 unit of this, you will make this amount more money. So if you change this equality to greater than equal in the objective function, it would increase.
In the D part, instead of having 2 production methods and producing equally, if we had a kind of constraint in which, if you want to produce 1 unit of Primrose, then you also have to produce like 1 unit of, say, English something.
Okay.
So what would happen in that case?
I'm not sure if you can solve that easily.
Because you're producing the same thing by using 2 methods, so you can divide it by 2.
I'm not sure if you can use it. You can use this method. I don't know. I have to think about it. It's not that straightforward like this. Remember, not all the questions are answered for dual variables. Some questions are answered, some questions are not answered. Okay.
We never know. You may be able to solve it finally.
I'm going to think about it, and if it's a nice answer, I will play it. It's not that this is standard. I'm sure.
This would come in the final once again.
Linear program. That's what I'm not sure. You should ask for a second. So now we have 5:35. Now this really took a little bit more than what I thought. Because we talked a lot. Now we have half an hour to solve the last question, which I'm pretty sure that it doesn't need half an hour. I agree it was a long first exam, so don't worry. And I looked at I haven't graded all of them, I have just graded some of them. And you have all done the same, so don't worry. There isn't a big difference in, yeah, it's equal, so.
Equally screwed.
No, not really equally screwed up. It's equally.
For this much.
More standard deviation.
It's equally acceptable. Let's put it that way. Now, this is a kind of question that I think it arises in production planning a lot of times we see it. So you have an asset which return on it is a function of the amount that you invest in it, and it's non-linear. So basically, if you invest this amount, the return is this amount. If you return this amount, the return will be this amount. So it's a piecewise linear, not linear. And basically, it's saying we want to solve this problem. Maximize sigma I equals 1 to n. I'm going to explain what I mean by this. Sigma xi less than or equal to w, xi greater than or equal to 0. So this is one of those RIXIs. So each of the elements here look like this. They are a piecewise linear thing. Okay? Now we want to maximize the return on these guys, subject that we have a certain amount that we can invest and not more than that. And the question is, how do you do it? Basically, the first step tells you how to do it. So the first step says, okay, I need to write down these numbers here. AI1, AI2. So this is the slope for the first part, this is the slope for the second. And this is Li, limit for I. Okay, good. It says show that x is greater than or equal to 0, Rix equals minimum of A1ix and AI2x minus AI2 minus AI1 Li. Before we're looking at it, what it means is this. These two are equations of two lines. One of them is this, the other one is this. Okay? So what it's telling you, it's saying that the return, which is this function, is the minimum of the amount on these two lines. So by looking at the picture, it's totally obvious. At any point, you look at the value on those two lines. The minimum is here. Here, the minimum is here. So basically, it's just what the in picture is trivial. So it's just asking you to do it on math to show that the return, which is this function, is nothing more than the minimum of these two values. Okay? Is it clear or no? Now let's see how we do it. We assume that x is less than Li. So we are talking about x which are here. What's the return? The return would be Ri of xi would be the value here. AI1 xi. Xi. Okay? This is just look at the return on the return function. Now, look at the value on this line. Let's call it 1, let's call this 2. So value, 1 value. The value of 1 is still the same thing. AI1 x1. Look at the value of x that is here at this point. It would be... Now, we need to write down the equation of this line. We know that... So, do we know the slope at this point? How did I write the equation of this line? Just give me a second to remember how I wrote down the equation. Okay. What's the value of this point? It's the Li and AI1 Li. So this is the coordinate of this point, whether it's this line. So from this point, I draw a line with this slope. Let's see what's the equation of that line. The equation of that line would be y equals AI2 multiplied by x. Oh, sorry. Y minus AIL1 would equal to the slope, which is AI2 minus x minus Li. So this is the equation of this line. If you rewrite it, y would equal to AI2x plus AILI minus AI2Li. So this is the equation of the line here. So the value of line 2 at a point here would be AI2 xi plus AI1 Li minus AI2. Okay? Now, we want to make sure that the minimum of these two equals to this value. How do we make sure? We just need to know that which one is greater than the other one. There are different ways to claim it. I'm going to claim it in this way. Let's look at it like this. We know that AI2 is less than or equal to AI1, and we know that x is less than or equal to Li, because that's what we chose. So from these two we will get AI2 multiplied by x minus Li is greater than or equal to AI1 multiplied by x minus Li. Why? Because this is less than this. X minus Li is a negative number, so I multiplied both sides of this by a negative number, I flip the sign. This, and after simplifying it, you will get AI1 2 xi this term, then multiply it by this guy, bring it there, plus AI1 Li minus AI2 Li is greater than or equal to AI1 Xi. So by just writing these two, multiplying it, rearranging it, we got that this number is less than this number. So the minimum of these two will be this guy, which is equal to this. You can do exactly the same argument by Xi greater than or equal to Li, the sign would flip, the minimum would be here, not here, and you got to that. So then you have shown that if you look at those two lines, it's something which is clearly obvious from the picture. You have just shown that if instead of just working on this function, which is a piecewise linear function, you can just look at these two linear functions, always take the minimum, you would be there. Okay? So this is the first step. Now the second step is that using the resulting part A, which is this minimum guy, instead of writing I, write it as a minimum of two linear functions, then linearize the problem. So here you would write maximize sigma minimum of AI1 xi and AI2 xi minus AI2 minus AI1 li. Okay? And then the same constraints, nothing changes. So instead of looking at maximize this sum, we know that Ri equals to this minimum, so we are using this minimum. And we know how to deal with minimum of the linear function. We call this alpha. Alpha is not good, it's going to mix with 8. Let's call it beta. We have beta here. So we call it beta I because for each of these i's you would have the same thing. And then you would say maximize sigma beta I given that beta I is less than or equal to AIXI, given that beta I is less than or equal to AI1, AI2XI minus AI2 minus AI1 Li for all I. And you will have xi greater than or equal to 0, and you have sigma xi is less than or equal to 10. Now this would be a linear case of this non-linear. That's it. Okay, so we finished in 6:45, 5:45. It was a little bit long, right? But still, it wasn't that hard. You really don't need to worry about your grade. So, any questions?
When are we going to be told our grades?
Okay. So, the grade, I think I'm going to finish my part of grading by tonight and give it for Bangor tomorrow. So maybe on the Monday, you'll get it done.
Which day is it?
I don't know about that.
Anyway.
I have to to tell the class tomorrow, so I guess it's not. I think it's the last day of class, but I'm not sure.
We will do quadratic programming with you.
Huh?
You are going to do the quadratic programming also?
Yeah, review it.
Review it.
Yeah, I will do it. Because I didn't have any homework for this. And I didn't want to, just do something without even having looked at the homework. So I will good look at homework because I think the review on Monday would be a long one.
Homework is posted tomorrow.
Yeah. This last one, okay, we can go over it. Why not?